Here we go with some more integration. So our first question here is clearly a partial fractions problem. The clues, of course, it's got linear factors on the bottom. It's not top heavy, so it's quite a nice one. So let's first of all rewrite this in terms of partial fractions. So we've got 5 plus 3x over x plus 2 x plus 1 squared is going to be equivalent to a over x plus 2, that's the first factor, plus b over x plus 1 plus c over x plus 1 squared, which of course rearranges to 5 plus 3x is equal to a times x plus 1 squared plus b times x plus 1 x plus 2 plus c times x plus 2. Now, if we start off by considering x equals -1, then that gives us 5 minus 3, which is of course 2 on this side, and on this side the a term and the b term vanish, leaving us with the c term, which is c times 1. So there's our first constant. Now we're going to consider x equals -2. That's going to wipe out the c and the b terms. So we've got -1 on the left hand side, and on the right hand side we've got -2 plus 1 is -1 squared, plus 1, so that's just going to be a. So that's our second value. And now we're going to use these two and a third value of x. I'm going to choose 0 just to make it nice and straightforward. So on this side we just have 5. And on this side here, when x is 0, a is just -1, because you have positive 1 here. When x is 0, we're going to have 2 times b, so positive 2b. And over here, well, c is 2, so it's going to be plus 4. And that means we can have, that rearranges to 2, and it's the same as 2b, which means that b equals 1. Which means I can now rewrite my integral. So, let's go there. We know who likes doing arrows, don't we? There we go. Right, so this integral is the equivalent of a is -1, so it's -1 over x plus 2. b is +1, so it's +1 over x plus 1. And c is positive 2. 2 over x plus 1 squared with respect to x. Okay, so that's the first bit. Now what we've got here, well, we've got a this is going to be a log, because we've got minus ln of x plus 2. This is also a log, plus ln of x plus 1. Now, attempting to see this as a log, don't forget that what you've got here is 2 times x plus 1 to the -2. And this is a standard pattern. We can try x plus 1, add 1 to it, you get -1. When you differentiate that, you get -1, it comes down, that differentiates to 1, so it's minus x plus 1 to -2, which of course is pretty similar to what we've got here, which means that when you integrate this, you're going to get -2 times x plus 1 to the minus 1. And don't forget the plus c. Now, not essential, but worth remembering that these two logs here can be combined using the division rule. And then we've got 2 over x plus 1 plus c. And there we go. Okay, second one. Well, what have we got here? We've got several tempting looking it looks quite similar to some of the trig identities, but it's not really, is it? It's quite close to the Pythagorean one. I think the thing to do here really first is to multiply it out. So we consider that as being equivalent to sin x plus cos x times sin x plus cos x with respect to x. So we get sine squared x plus 2 sin x cos x plus cos squared x. And if I rearrange that and bring the sine squared x and the cos squared x next to each other, and then we've got our plus 2 sin x cos x there. Okay, so we're going to use two identities here. I think it's fairly obvious what we're going to use. First of all, we're going to use sine squared x plus cos squared x equals 1. So that's these two here. So we're going to have the integral of 1. And then this one here, we're going to use a double angle formula. And it's very common to use a double angle formula to end up with a single sine or cos. In this case, we're going to use sine 2x is equal to 2 sine x cos x. So there's our identities. So this is going to become plus sine 2x with respect to x. And then we can actually integrate. So one is going to integrate to just plain old x, and sine is going to integrate to negative. The 2 comes out as a half there, so negative a half cos 2x plus c. And if in doubt, differentiate to check. Okie dokie. Well, fairly standard parts looking integral here. Notice the two things multiplied. You've got the e function and the x there multiplied together. You should recognise this hopefully. So this is integration by parts. So unless you have an ln, your u should be your x term, which makes du by dx equal to 1, and dv by dx is going to be e to the 2x, and be very careful about this 2, that makes v equal to a half e to the 2x, which you can check by differentiating. Remember, the 2 is going to come down, and if you're not sure, you do using the chain rule. Okay, so let us go ahead and use the parts formula. So uv first of all, so that times that, so it's x over 2 e to the 2x. That's our uv, and there's our limits on the uv. Okie dokie. So then we're going to subtract the integral of v du. So v is that, du is 1, so basically the half can come straight outside of the integral, and we've got e to the 2x with respect to x. And that's going to end up very straightforward indeed. 0 and 1. We shouldn't forget our limits, should we? And we've got minus a half, and then in here we've got a half e to the 2x, of course, between 0 and 1. Of course, we could take out our half there as well. Okay, so now we just stick in our limits. So first of all, we've got our 1, so the 1 is going to become, in this one, we've got 1 over 2 e to the 2 times 1, and that's going to, when the 0 goes in there, it's going to wipe it out, so we've just got that. over here, let's bring our other half out. So we've got a quarter now, which leaves us e to the 2 times 1, and then we're going to subtract e to the 2 times 0, which gives us that. So we have a half e squared minus e squared over 4 plus a quarter, because e to 0 is 1, and 1 times a quarter. A half take away a quarter, because these are like terms, is going to leave us with a positive quarter. So we've got e squared over 4 plus a quarter. And that's that. Okay, last one. Okay, so this is a substitution. We're given the substitution here. So we've got u, so let's get du by dx. Okay, so the 1 will disappear, cos goes to minus sine x. Let's do our limits. If x equals pi over 2, then u equals cos pi by 2 plus 1, which of course pi by 2 is 90, so that actually goes to 1. And if x equals 0, u equals cos of 0 plus 1, which is 2. Really doesn't want me to draw it there, does it? There we go. Okay. So we can now rewrite our integral in terms of u. So the 0 has turned into 2, and the pi by 2 has turned into 1. And then we have e to the power of u times sine x. Now, dx, if we rearrange this, is going to be equal to du over minus sine x. So over here we've got dx, and we're going to substitute du over minus sine x. And of course you can see there that they're going to cancel, leaving us with the integral of minus e to the u with respect to u. And we can remove the minus sign and switch the limits. And that is going to give us, of course, e to the u between 1 and 2, which is e squared minus e. And that's that. It's worth saying that if your layout of your integrals differs a lot from what I'm doing, then you should seriously look at trying to copy my layout more. It doesn't have to be identical, but this sort of layout is pretty common. You should certainly be bringing your limits down with you and not losing anything. If you're going to be using one of the formulas, you should be collecting all your bits together and being very systematic and well laid out about it. Hope it's going well for you.